Hi, I'm Inseung Hwang from KAIST in Korea. In this video, I present portable acquisition of Polarimetric SVBRDF and shape with unstructured flash photography, so-called Sparse Ellipsometry. Light is an electromagnetic wave. The direction of oscillation is perpendicular to the direction of the wave. Polarization is the direction of the electric field. Polarization has been widely used in many computer graphics and vision applications to estimate high accuracy reflectance and high detail normal. Also, it has been used for acquiring depth, de-hazing, and realistic image editing. However, none of these methods could obtain the full Mueller matrix of polarimetric reflectance and geometry simultaneously on 3D objects. The light transport of polarized light can be defined in terms of Stokes vector and a Mueller matrix. A Stokes vector has 4 elements. The first element is the light intensity, and the second and third elements are the components of the linear polarization, and the last one is for circular polarization. A Mueller matrix describes the transformation of a Stokes vector as a 4x4 matrix through light reflection or transmission. Then, how can you obtain the Mueller matrix when the polarized light passes through? Ellipsometry is a polarimetric reflectance method that acquires a Mueller matrix through light interaction. An ellipsometry system consists of polarizing optics for light and analyzing optics for sensor. Then, we need to capture many samples by rotating optical components. Lastly, we regress the unknown coefficients of Mueller matrix through optimization. Ellipsometry requires dense samples of geometry and polarimetric angles of optical elements. The existing image-based ellipsometry has been built in a very professional benchtop setup, the calibration of which is very fragile. It takes 2 to 5 days to capture one single material and can handle perfect sphere object. To mitigate these challenges in existing method, we propose a handheld device that allows us capture in 20 to 30 minutes. And our method enables acquisition of polarimetric appearance in various shapes. Here is an example of our method. Here is an example of our result. The captured Mueller matrix of a 3D object and its novel view and light rendering. Now let me explain our method. I'll explain our polarimetric BRDF model first. Polarimetric reflection can be described as a Mueller matrix. However, all the components change depending on incident and excitant angles. Our PBRDF models consist of 3 terms: diffuse reflection, specular reflection, and single scattering. For the diffuse reflection, we account for the light transmission to the medium, multiple scattering that loses the polarization properties of the incident light, and lastly, the transmission from the medium. Our model accounts for a single bounce reflection following the traditional BRDF, but with the addition of coordinate conversion with respect to half-wave vector of microfacet normals. Different from the existing PBRDF model, our model takes single scattering of polarized light into account. Our full version PBRDF model account for the light transmission to the medium, shallow scattering as a single bounce, and lastly another transmission from the medium. And thus, the Fresnel effect occurs many times and it requires a highly complicated coordinate conversion, resulting in severe ill-posedness in inverse rendering. And thus, we introduced another practical solution for the single scattering, specially designed for polarimetric inverse rendering. We obtained that the polarization state of single scattering is very similar to specular reflection, while having very different roughness against specular reflection. Also, we found that single scattering albedo present color even for dielectric surfaces. This is our device. We combine an off-the-shelf polarization camera and a flashlight equipped with a linear polarizer. For input, we captured about 100 to 300 flash photographs as shown in this video. In the given setup, the light and the camera are oriented in the near same direction. A Mueller matrix can be simplified in the coaxial configuration. The blue term means diffuse shading. The green term indicates the sign component of diffuse polarization. The yellow term means the cosine component. Lastly, the red terms are specular and single scattering component. In this work, we focused on measurement of linear polarization only, so we reduced the dimension to 3 by 3. Now let's denote these notations as abbreviation for simplicity. As we employ a polarization camera as input, it captures linear polarization state at 4 different angles. Our captured input includes diffuse shading, the sign component of diffuse polarization, and the mixture of specular and single scattering with cosine components of diffuse polarization. Once we capture input images, we optimize shape and polarimetric appearance in an iterative manner. We obtain a rough base geometry by CoMap. We then update the PBRDF model parameters, surface normal, and geometry per vertex. On the last updated geometry, we fine-tune the PBRDF parameters to complete our optimization. Our loss function consists of 4 different terms designed with respect to refractive index, diffuse reflection, specular and single scattering, and normal. Here is our refractive index loss, that is the summation of the square difference between the observed and predicted degree of polarization. The DOP of the diffuse reflection depends on the refractive index and normal orientation. Generally, the DOP function increases monotonically. Second, this is our diffuse loss, which indicate the difference between the observed diffuse shading and predicted diffuse shading. This evaluates the photometric consistence of diffuse reflection. This is a specular and single scattering loss, where the first term is about the difference between the observed and the predicted specular and single scattering. Since the number of observations of specular reflection is insufficient, we devised a novel augmentation scheme in twofold. We first regress the model parameters by clustering observation in similar materials, and then generate more samples to augment specular and single scattering observation in this second term. It enables us to estimate specular and single scattering parameters more robustly and accurately. The last term is surface normal loss, which indicates the difference between the observed and predicted azimuth angle of normal. Here we validate our model with an existing PBRDF measurement dataset. We propose a full PBRDF model and a practical model. As shown in this video, Both models predict the physical measurement of the PEEK material with high accuracy. Here we compare our model prediction and the physical measurement of the red billiard ball. In the light intensity and the diffuse shading components are close to each other. We compare the measured and predicted mixture of single scattering, specular, and diffuse polarization. We also compare the difference in diffuse polarization. Both present a very good agreement. In the last column, we compare the 1-1 component of the Mueller matrix that consists of the colored single scattering and the specular reflection. The physical measurement and our model prediction are very close to each other in terms of single scattering and specular reflection. This table shows the physically measured and the predicted refractive index values in the PBRDF dataset. While our takes less samples, the estimated refractive index values are very close to physical measurement. In inverse rendering, specular reflection parameters are easily underestimated due to insufficient specular observation. As shown in this plot of the sample point, the estimated roughness function using our specular augmentation scheme can provide a more highly realistic appearance of specular reflection than the conventional approach. Now we present results of the real object. These are photographs and scanned geometry of a captured ceramic object for reference. A result of Namedar suffer from overfitting artifact in overview and light rendering. A result by Beck et al. Also have artifact of rendering result and normals. The last one is ours. Our method can obtain the geometry and appearance with high fidelity with respect to ground truth. Now let me show you more results of our method. Our method captured the very realistic appearance of the ceramic object that includes smooth and rough surfaces. Here is another object. Matryoshka door is covered with glossy paint and it has a simple geometry. It presents strong single scattering and also the reconstructed result represent its glossy surfaces well. Here is the other result. The chicken figure is covered with matte paint and it has bumpy structures on the surfaces from wood texture. It presents strong single scattering. Here we compare single scattering and angle of linear polarization for a real and fake orange. Despite their similar appearance, polarimetric information allow us to distinguish. Our method is not free from limitation. Due to configuration of polarization camera, we focused on linear polarization only. The retardance property of metallic surfaces make model very complex, and thus we focus on dielectric surfaces only. We found that our DOP term is very sensitive to noise because of the division factor by diffuse shading. In particular, dark surfaces sometimes suffer from artifact. In this work, we have presented sparse ellipsometry that can capture the shape and spatially varying polarimetric reflectance. The acquisition time is significantly shorter than the state-of-the-art image-based ellipsometry. We also proposed a new PBRDF model that accounts for diffuse, specular, and single scattering. More details are available from the project website. Thank you for your attention.